Here we have something a little bit different than the previous examples, and it's different in two ways. Number one, we have a 3/2 exponent in the denominator, and number two, we have a trinomial in the denominator. What we've got is the integral of x squared over the quantity of 3 plus 4x minus 4x squared to the 3/2 power dx. I remind you that the 3/2 power means it's a square root that's cubed, and so we do have a square root here. And in thinking of our patterns for trigonometric substitution, we're generally looking at something like the square root of a squared minus u squared, or plus or u squared minus a squared. I'd like to point out that the u squared portion can be considered to be u as a function of x. That's what we have in this case. Our goal can then become to express the radicand, or the base of the expression that has the 3/2 exponent, as an a squared minus a thing quantity squared with, say, parentheses. So let's consider 3 minus the quantity of 4x squared minus 4x. Now I've left a little bit of a gap here and there in what I just wrote. If we consider completing the square inside the parentheses, we have 4x squared minus 4x. And if we think about it for a couple of minutes, then it will make sense that if I add 1 inside of the parentheses, then I will be completing a perfect square trinomial. Adding 1 inside with a minus in front of the parentheses means that I've really subtracted 1, and so I need to add 1 to the 3 outside of the parentheses. Simplifying, we get 4 minus the quantity of 2x minus 1 squared. That will fit the pattern of our a squared minus u squared. I can then rewrite the integral as the integral of x squared over the quantity of 4 minus the quantity of 2x minus 1 squared, whole denominator to the 3/2 power dx. Before I continue on, I'm going to talk about this plus 1 that we put inside the parentheses here. Folks, we had 4x squared minus 4x, and I basically magically said, hey, if we add 1, everything works. I'm looking at the coefficients of 4 in front of x squared and 4 in front of x, or negative 4. Folks, if we had x squared minus 4x plus 4, I think it'd be fairly clear to us that that would factor into x minus 2, the quantity squared. We essentially have the same coefficients, they're just occupying different places, right? Instead of 1x squared, we have 4x squared, and then instead of plus 4, we have plus 1. It still fits the pattern of this perfect square trinomial. Now, let me set this aside. You also may wonder how I knew this was going to be a subtraction and not an addition, because how did I know this wasn't going to be a tangent situation, right? I used the coefficient of the x squared term. It was negative 4x squared, and so I factored a negative out in front of the whole thing. At this point, what you have is an integrand, the denominator of which fits the pattern that we can use for a trigonometric substitution. And so I'd like you to pause this and see if you can come up with the substitution and evaluate the integral. So how'd we do? The denominator, the base, is 4 minus 2x minus 1, the quantity squared. So 2x minus 1 is going to be the vertical side of our triangle. The hypotenuse is going to be the square root of 4, and so 2, because I have a subtraction in that radical and the variable is coming second, I know I'm using the sine of theta. So the sine of theta is equal to 2x minus 1 over 2, which means that x is equal to 1/2 times the quantity of 2 times the sine of theta plus 1. dx is going to be cosine of theta d theta. Using the triangle, the third leg of the triangle, I went ahead and went with the original radical, square root of 3 plus 4x minus 4x squared, and that equals 2 times the cosine of theta. Making our substitutions, we end up with 1/2 squared in the numerator, 2 cubed in the denominator, that's all going to combine and become 1 over 32 outside of the integral. Because the numerator had an x squared in it, we're squaring 2 times the sine of theta plus 1. And so we have 4 sine squared of theta plus 4 sine of theta plus 1. Replacing dx meant we were using cosine of theta d theta, and replacing the denominator with 2 cosine of theta quantity cubed means that we end up with overall the integral of 1 over 32 times the integral of 4 times the sine squared of theta plus 4 times the sine of theta plus 1, all divided by cosine squared of theta d theta, because 2 factors of the cosine divided out. Sine squared of theta over cosine squared of theta can be replaced by tangent squared of theta, and the sine of theta over the cosine squared of theta can become the secant of theta times the tangent of theta. 1 over the cosine squared of theta is simply the secant squared of theta. Using a Pythagorean identity, we can replace the tangent squared of theta that has a coefficient of 4, so then we have like terms. 4 times the secant squared of theta plus the secant squared of theta then becomes 5 times the secant squared of theta. The rest of the integral, total we have 1 over 32 times the integral of 5 times the secant squared of theta plus 4 times the secant of theta times the tangent of theta, and then having distributed the 4 with the Pythagorean replacement for tangent squared of theta, we get minus 4, all of that d theta. Integrating the secant squared gives us the tangent. Integrating the secant tangent gives us the secant. So we have 1 over 32 times the quantity of 5 times the tangent of theta plus 4 times the secant of theta plus 4 theta plus c. We again need to express our answer in terms of x, and so I will again bring to mind the triangle that we had. 1 over 32 times the quantity of 5. Tangent of theta is 2x minus 1 divided by the square root of 3 plus 4x minus 4x squared. Secant of theta is 2 over that square root. The secant of theta has a coefficient of 4, and so we write plus 8 divided by the square root of 3 plus 4x minus 4x squared. And then we have plus 4 theta. I think the easiest relationship to give for theta is that it is the inverse sine of 2x minus 1 over 2. All of that plus c. We have 2 fractions that have the common denominator, and simplifying those and then distributing the 1 over 32 will give us a final answer of 10x plus 3 divided by 32 times the square root of 3 plus 4x minus 4x squared plus 1/8 times the inverse sine of x minus 1/2 plus c, writing that argument of the inverse sine function just a little bit simpler. And there we go.